let's see. What I want to do is work with you today, and orbits are so important that we've talked about it a lot, but I want you to understand and know how to go through, given certain parameters, how to find them. And most of those parameters are in those sheets that I give you from the SMAD book. But you ought to know how to calculate those. So tell me, for example, what is at least one parameter on a satellite that you've got to be given, or a couple of parameters that will allow you to define exactly what the orbit is? Altitude. Okay. So this we've got to be given, right? So this is given. What else must you know?
Azimuth.
Pardon?
Azimuth.
Azimuth? What do you mean azimuth?
Like maybe elevation, degree.
Well, but we're talking about the satellite. Okay? What else? What have you got to know about its launch orientation with respect to the sun? You got to know, there's the two kind and everything else is in between. Noon, midnight, dawn, dusk, right? So you've got to be known, you've got to know the orbit. Let's say launch. Yeah, launch time. What else must you know? There's just one zero. Don't you need to know that? What does that tell you about the orbit? That's right. That's right. Okay. What else must you be known? How about right? You have to know that. It tells you a lot about it. Okay, now let's make some assumptions here on this satellite. It used to be BeakerSat, it was Eagle 1, and now it's officially T-Logo Cube. But you know what it is? I don't mind that name because I would call it TLQ.
That's how it's better.
All right, we'll call it the TL Cube. TLQ. Okay, what is the altitude of TLQ roughly? It's what?
About 700 kilometers.
Actually, it's less than that. The last, I thought it was going to launch at that, but I seen something like 619.
Oh, that's even better.
Okay. Oh, what about the launch time? I'm not sure, but I think it was a noon midnight. So should we say that? So noon. Okay. Roughly what's its eccentricity? If it is a circle, what is the eccentricity? Okay, so we think it's 0. What is the inclination? Okay, it is a sun synchronous. So it's over 90, right? So we'll say 90 plus. Okay, go to your tables there, your SMAD tables, and let's look up a sun synchronous satellite. Can you calculate the inclination based on this thing being sun synchronous? When you find a table, what do you see? You find the table here, and I think probably what you'll see is you'll see altitude of 600 kilometers, 650, and 700. Right? that sound right? Do you see any for 619? Is there anything for 619? What do you do? How do you find it? Okay. Oh, that's another parameter. Orbit Life. Okay.
The estimated orbital life.
Okay. What's the estimated orbital lifetime? What must I know in order to determine roughly what the orbit life is? Okay. So for the orbit life here, now this is inclination up here, and life. I need to know what?
How many kilograms was it again?
Max or min, right? Max or min what?
Solar activity.
Okay. There's also another parameter there. What is it? Ballistic coefficient, right? So it's a function of both the ballistic coefficient and the solar flare activity, right? So what happens with the solar flare activity?
Whenever the sun hits the Earth, it makes the atmosphere heat up and expands.
Does your satellite come down sooner or longer? Shorter or longer?
Shorter.
Okay. What about ballistic coefficient? What is the ballistic coefficient shown there? What is the number there? Isn't it area over mass? What is that parameter that's shown at the top of the table? Where is lifetime? If you look right here, oh, it's weight over that's kilograms over area, essentially. kgm max. Okay, so yeah. So it's kgm m squared. kg over m squared. Well, what does that mean? If you look at a given satellite, what do you need to know about that? Is it a bowling ball or is it a soccer ball? Is telling you what? So, okay, so what about the cross-sectional area of a bowling ball compared to a soccer ball? About the same, right? Okay, so this is the cross-sectional area. This is the weight. So if we have a soccer ball, what is the soccer ball or a bowling ball? What is the relative relationship between those for the ballistic coefficient? The only thing that changes between the soccer ball and the bowling ball is what? The mass of it, right? The weight. So what we can say, if the cross-sectional area is the same, we can say for a ballistic coefficient, we can say that the soccer ball is less than the bowling ball, right? Does that make sense? Okay. Now, like we did, you've seen what we did on TLQ. We did something on it to increase its, to decrease its life. What did we do? We put drag brakes on it, right? So that affected what? That affected the surface area, right? So if I can increase this, is that right? If I can increase this, then my life is going to be shorter. Does everybody agree? Do you see what we're saying there? Is there anybody that has a question about that. If I increase the area, I got more drag, right? Gonna decrease the life. If I increase the mass, it's gonna last longer because the energy that I took to put it up there is greater than the energy if it weighs less. Does that make sense? Okay. All right. So, how do we know what the ballistic coefficient to use for TLQ? I have two choices on the table, right? Don't I have two choices on the table? Where's the table? Right there. Okay. Kilogram over mass. Is that mass cubed?
Yes.
Yeah, it's cross-sectional area, so it's squared. Okay, I have two choices for each solar activity. Atmospheric density. Well, that does. Where's the decay rate? You haven't got either one of them here, have you? Where's the decay rate?
I'm not sure.
Oh, let's look. Orbit lifetime. Okay. So, what's the choices I got for ballistic coefficient? 50 or 200, right?
Yeah.
Okay. What do you think TLQ is? You gonna pick 50? Okay, so we'll say that here, the ballistic coefficient, for as far as the table is concerned, we're gonna say 50, right? And what about the solar flare activity? Is that AIR, or ARE? Okay. Are we at a max or a min?
Let's say max. I mean, you can do worst case scenario and go max. Always.
Yeah. Worst case scenario. Okay.
What do you want to do best case scenario if you're trying to calculate lifetime? You want it to be as short as possible.
Well, normally you want it to be as long as possible. What's our criteria for making it short as possible?
It has to be lower than 23 years.
It has to be below 25 years because of the FCC. Space junk people. That's right. Okay. So, solar flare activity, you know what? I think the solar flare activity is at a mean. In between. Not high, not low. So I'm going to just say mean. Okay? So we got parameters here and things that we have to calculate, right? Or find. So we have to find this. We have to find that. Okay. Well, let's go back to this. Let's go back to the inclination that we need. You don't have it in the table, right? You don't have 619 in the table. What do you have for 550? For sun synchronous, what's the inclination for sun synchronous at 550? Look it up in the table. 97.40. What is it for 600? 97.79. 650? 97? 7.99. 700? 98.19. How are you going to give me the best estimate for 619?
Average.
How about plot that? Okay, can you plot this? Okay, here is 550, 600, 650, 700. And we're going to plot it up here. This is the lowest. So I'm going to say this is, it's all nine, this is 997.098.0, right? Where's 550 at? 97.4 right here. You buy that? Where's 5? 5 is about right there, right? Okay, 600, 97.79. My guess is with this rough curve, it's almost 8. So it's right in there, right? And then the next one at 650 is just right in here, right? And 700 is just above it, right? How do you find 619?
You find the slope of the 2 points, and then you use the formula y minus one of those y points.
Look at the chart. Guess it. What do you? Where's that going to be? Is it going to be there? 2.5? Right in. I'm going to say right in there someplace, right? Okay. And then if I think my thing here's not too good. So, right in here, look. What is that?
97.82.
97 what?
0.8.
He's saying 97.82. Does everybody believe that? 82. 97. Okay, I'll buy that. But what's a way to do it more accurately?
You create a formula for the line.
What you do is put the line in Excel, and in Excel you can say, here are all of these different kind of formulas. Which one matches this line the best? And it'll give you the formula for it. Then what you do is put in 619, and it'll tell you what the inclination is. How many of you can do that?
Also, when I was Googling, there's actually an online program that if you give it those 2 points, it'll create the line. That was when I was trying to find that formula.
Okay, so how many of you know how to take Excel, put the points in for that you've got off of your chart, and have it plotted? Do you know how? Okay. How about you two?
It's awful.
I can kind of do it, yeah, but I can't
Okay.
tell me what it-
It's been forever since
Okay. Forever? We're going to be doing that. Okay. Everybody in here has raised their hand, I think. How many people do not know how? Or what make difference does it make whether the guy on this side or that side, whether you raise your hand? We're going to do that. Okay, for right now, this is the way you do it. You do it the Twiggs brute force method. You know, you just chunk those numbers in there and take a while. What is this thing? What's a YAG? Oh, that's not right. It's a swag. We won't, since we have ladies in the room, we won't tell you what it stands for. But it means guessing, right?
Yeah.
Okay, so now we got this one right. Let's find the orbital lifetime. We got 619. Give me the estimated orbital lifetime. How do you do that? Look at the table. Can you, for each of these altitudes, for the ballistic coefficient we've checked, for the solar flare activity, can you find orbital life for these numbers?
roughly.
Yes, right? Yes? And then how do you find out what it is at 619?
Yes.
Swag it. Swag it. Okay? That ain't too hard, is it? Okay, so we're going to swag it. Give me a swag.
About 2,500 days.
2,500 days.
Well, it goes up really heavily because it's 600. It's 16.
Yeah, it goes-
16, 13.
I know, boy, you get up there a little bit up in that upper thing and it just really goes. So what have you got to do? You got to plot a curve. Is it going to be a straight line? Oh, no. No. Right? Oh, it's changing like crazy, right? Okay, so now what we've done is we've used this and this to get this, and we've looked it up and we got that. We know the eccentricity, we know this, we know that. Gosh, we got so much data here, we just don't know what to do. I will guarantee you, you will have to do this on the final exam. You can use any resource that you need except another person. And I will guarantee you that the altitude will not be on the table. Okay. Now what else would we like to know? What about orbit time? What about orbit time? How can I calculate the orbit time?
You mean like time it takes to complete like a full orbit?
Right. What is the orbit time for one orbit?
Calculated velocity from this altitude.
So I can use the altitude to calculate velocity, and I can, from the altitude, I can calculate orbit length, right? And to calculate the orbit time. Is that enough to do it? Okay, it's zipping around there. All you got to do is find out at that velocity how long it takes you to travel that distance. And you got what? What? Orbit time. Orbit time. Okay, now you got orbit time. Question is, here I got the Earth. Okay, and this guy essentially, let's say you're here in Kentucky at about 38 degrees latitude, right? Do you know what the longitude is? No, that's a fair answer. That's a fair answer. Okay, you're here at 38 degrees, and this thing is going to kind of, there's the pole. This thing is going to kind of be like that, right? As it makes a pass. It's going to come, if you look straight north, the pass that comes over here during the day is going to go from a little bit southwest to a little bit northeast, right? Does that make sense? Right? Okay, so here you are, and what's happening to the Earth as this thing is going around?
Spinning up.
The Earth is rotating, right? So let's say what you get is you get a pass here. Here's Moorhead, and over here you get a little pass that goes blip. Okay? Why? It's over in the east, right? The orbit is not right over the top of us. Then I might get bleep, and I might get bleep, and I might get a little bleep here. Now, you know what a bleep is, right?
Time we can see the satellite.
Absolutely. Absolutely. Can you tell me? This is the easiest one to do. So I'm going to be nice to you. I'm going to let you do the easiest one. Can you tell me this? What is this? And this is, by the way, the one that comes over the top of you is called a zenith pass. Okay?
Is it the maximum?
That is the maximum. So how do you calculate this? So I want max view time. How do I calculate it? Anybody? Okay, here we go. Yeah. Here is the Earth. Here is the orbit, very exaggerated. If you looked at the Earth, and by the way, what's the radius of the Earth? A lot?
Half the diameter.
Gosh, this guy, he's running on hard Pepsi today. How are you going to find out?
I could ask Siri.
Huh?
I could ask Siri. I can Google.
Google it, right? So are you going to have to bring your computer? All right. So let's say I think it's somewhere around, and I don't know for sure because I'd have to look it up, but I'm going to say 6,500 kilometers. Okay? And the altitude is this little distance here, which is 619 kilometers, right? Now, I want to calculate the pass time. Well, when I first see the satellite as it's coming around, let's say it's going like this, the first time I see the satellite is when it's right at the horizon, right? Okay, how far is that? What's the distance from the first time you can see that satellite? How long does it take that satellite to pass over? Well, I know here that my orbit time is roughly what? Did we figure that? It's always roughly 90 some odd minutes. I'm going to say 93 minutes. And what this is this is... Oh no, it's Bob's swag.
So we can use that.
No. It could be Matthew's swag.
Yeah, no.
Now, it depends on how close you are to it, whether I give you credit or not. Okay. Look at that. Can you determine the pass time, the view time? Well, look at this. Golly. What's this right here? Oh, I'm so glad it's a triangle. So, if I know this distance, okay, can I calculate the angles and the sides? So if I know this distance, right? And I know this distance, I've got two sides. Can I calculate the third side? Okay. If I know two sides, can I calculate the angles in the triangle? If I can calculate the angle in the triangle, I can do what? Let's do this. If I can calculate this, because I know this is the radius of the Earth. This is the radius plus the altitude, right? So I can calculate the angle, all right? And this angle is the same as that angle.
So you find the short side, multiply by 2.
So if I know 2 theta over the 360 degrees, right? It's this portion of 360 degrees. If I know that and I multiply it by the orbit time, what have I got? The time over that arc, right? And that's what? Maximum Maximum view time, right?
Yeah.
Okay, no problem. I can calculate this, right? Because I can get that. No problem. Now, let me ask you this. When I have a right triangle, it's really easy. Now, what if I have this? Here's my satellite right here. Okay, this is the distance that I communicate with my satellite. What happens when the satellite is here? Do I know the distance to the satellite? Just the altitude, right? What if it's there? Then it's what? It's a thing that looks like that. Right? It is, but it isn't a right triangle anymore, right? This angle in here is greater than 90 degrees. How do you calculate that distance for that? Use what? No, that only works with the right angle.
And use law of sines.
Huh?
You can't use law of sines. Nobody likes them.
So I think sines and I know it, at least this.
I don't know which. Law of cosine is just technically less sketch.
It's a squared plus b squared. No, a squared equals b squared plus c squared.
Okay?
2a plus.
If I tell you that the time between, if I tell you that the maximum view time is 12 minutes, okay? If you calculate the maximum view time is 12 minutes, can you tell me what the distance to the satellite will be in 6 minutes? After you first spotted it, 6 minutes. Where's it going to be? Right above us. I know that, right? But what if I tell you I want to know the distance up there 4 minutes after you first contacted? Use the law of cosines. Okay? My suggestion to you is that you make a spreadsheet that resides on your computer that you can calculate all these things. Is that a good suggestion? Or you can swag it and get lower grade. Okay. Look at all we've found there. Another thing, how about maximum eclipse? Do you know how to calculate maximum eclipse? Maximum eclipse.
Well, there is none. There's none for this one.
Noon, midnight? Oh, yes, there is.
No, that's a dusk dawn.
It's not going to tell you in there. You can only get swag numbers out of there.
Yeah, but I need to find it to get a... Take the earth and draw.
Okay, maximum eclipse. You remember? You remember this thing? Noon, midnight. I'm giving you the easiest one to do. No, the easiest one is what's the maximum eclipse time for a dusk done.
Oh, there's on.
You're right. The maximum you get is when it's rotated and your plane of your satellite is lined up with the sun, right? Okay? So, here's what I've got. There's the Earth. There is the orbit. And I've got the sun over here. And does the sun get parallel rays to the earth?
Actually, it's a little bit more curvy.
As far as we're concerned, it's so parallel because it's so far away and it's so big that you assume that the sun rays are parallel. And if we're noon midnight, then this is the eclipse area. Tell me how long your satellite is going to be in the eclipse area. Satellite, if it went in the eclipse here, what would be its altitude? If it went into the eclipse here, what would be the altitude? Right. Absolutely right. Because, you know, the Earth would be clear up here and it'd be 0. So that, what happens when you fly a satellite at 0 altitude?
It's the ground.
Okay, so how do you calculate this? Does this look familiar? Yeah. Does this look familiar?
It's kind of like the last.
Yeah, it's like the pastime, right? Okay. Is that important? Is the eclipse time important? How? On the power, right? Do you get any power generated in the eclipse? Yes, you do. You get some power that comes off of the infrared of the Earth. No, I don't think enough. But also when you're out in the sun, you get what's called the albedo. That's the sun shining and reflecting off the Earth. It turns out that you get I think it's this. When you're out in the sun, you get 650 watts per meter squared. When you have this old solar panel out here, like this, and it's shining right at the sun, you get 650 watts per square meter. Okay? It turns out that the albedo on the Earth while you're out in the sun, going back this way, shining on the backside of your satellite panels, at least over here where the sun is, you get about, I think it's somewhere between 30 and 35% of 1,650 watts per meter squared. But it only occurs in the daylight, right? Now, I lied. And I never do that at all, unless I can get away with it. On the backside, you get infrared. But the frequency of the infrared, your solar cells are not tuned to get power out at that frequency. But what you do get is you get heat. Okay? So you get 1,650 watts input to your satellite from the sun. If you have your solar panel there, you're converting some of that to electricity, right? But if you get the infrared coming up, then that's going to heat your satellite up. What do you think happens if I only have, I've got 1,650 watts, and I go into my solar panel, and I only have 20% efficiency on the solar panel? What happens to the other 80? Heat, and it's reflected. Depends on what the reflectivity of your solar panel and the place where you don't have any solar cells. So we're hitting both power system and thermal system today. Okay. Piece of cake, right? Piece of cake. Does it tell you anything? Look what you've learned. Oh my gosh. My gosh. You can go in and interview for a job and just know them completely. Right? You can say, I can tell you about the orbits, man, and get you a job that you're totally incompetent for. You better swag it, man. Or you better hit the books after you go to work, right? Everybody know how to do this? I wished you would get together in a study session with the class. Why don't you do that? Why don't you as a class get together as a study session? Do you have study sessions with in your other classes, voluntary study sessions? Those are good. I used to do that for the physics. I always used to get messed up on the physics exams. So we kept, in the dormitory I stayed in, we kept a file of every physics exam for the last 10 years. And what you found out, not cheating, but you found out, this old professor, he used the same examples over and over again in his test. So if you could work all of those examples, when you went in there, you would just ace that test. Is that a bad way to study? No, it's really good. Why don't you have a file on this class that you pass on to the new students that are coming in?
Are you telling us something about how you do your test?
No, I'm not telling you about cheating. I'm telling you about learning. So if you knew what I give on final exams for 120 for the last 3 years, would it help you? Do you think I would ever repeat a question from one year to the next? I did. I did. You seen all those questions I sent you?
I was looking at them, just like,
Yeah. Yes. I will guarantee you, yes. I will guarantee you, yes. Did I tell you what's going to be on the final? Yes. Will you learn? I just go like this and pour it in. Okay. This is the most exciting time I have had in my teaching career of having satellites launched and up there running. Is that cool? How many of you have been on the passes upstairs and heard that satellite or seen that satellite? That is the coolest thing, isn't it? Whoa. We're teaching real things, right? It's not as much bull as you thought it was, right? Okay, any questions? Everybody's squared away on it? You know how to swag things? That's all you've done all your life. Well, I have to tell you, I'm not the smartest bear in the crowd. So I use everything that I can to learn and understand and do things. And I do what I call brute force it. If I can't write an equation for it, I will brute force it. But I know, just by experience, of things that you can brute force it and get pretty close. For example, if nobody told you what the speed limit was on 64, what is the range you would pick?
45 to 55.
That's the fastest people go? What if somebody said, 64, Highway 64. Do you think you could guess what the average speed is? 85. Oh man. Anybody else? Hey, give me attention. What is the average speed on Highway 64?
75 miles an hour?
65 to 75.
It's what?
65 to 75.
65? No, I just want you to give me one number.
Oh.
75.
70.
What do you think? Now, why did you get that number?
That's the mean. That's the average.
That's right. Because you know that they don't go 90, right? Except once in a while. And then you'll always see them down the road with a cop after them later. They don't go along 45 except the guy that's going to breakfast with his buddies that are all 80 years old, right? So you can, that's the thing about engineering. You can know what are rational numbers. What if you punch in your calculator and you get an orbit time of 112 minutes? Or 1,200 minutes? You know it's not, because why? You know roughly what it should be. Yeah, do a Bob swag on it, okay? That's engineering, is knowing how to swag stuff. Don't swag too wide now. You narrow it down as much as you can, all right? Okay, I wish you the best on the test. And tomorrow, we'll finish up the lab we were working on.